Hello engineers, welcome to the new video of the course, and in this particular video we are going to understand that how exactly this shift in the biasing point, that is Vbias, changes the output signal. That means the output signal, you see, it is completely distorted, right? That means the lower part of the signal, it is clipped, right? We are going to see the reason behind it. In fact, this was my question to you all guys, where I clearly mentioned that when we are going to change this particular biasing point by 0.01 volts, then how exactly it affects the overall signal, right? I believe that you all guys have tried your best to think upon this particular idea. Now it's my turn to explain you each and everything in detailed way. So we are going to go step by step. Okay, so let's proceed further with this particular question. So very first reason for that is this, that is when VG of PMOS increases, let's say it increases by 0.01 volts, that is VG becomes 0.03 volts from 0.02 volts, right? Overall VSG decreases, thus the drain current ID also decreases. I know this might sound a little difficult for you to understand, but don't worry, we'll take one example for that. Remember, for PMOS, if VG is 5 volts then ID is 0, and if VG is 0 then ID is equal to maximum value. So if you could remember this particular point where I have explained you this particular example, so you see, let me just run this particular circuit. When my VGS, it is maximum, okay, one sec, sorry, VSG, not VGS, as it is, sorry, this is VG, my bad. When VG is maximum in case of PMOS, so this is my VG, right? This is my VG. Let's say this is logic 1, means let's say it is 5 volts, plus of 5 volts, right? So what is our VSG? VSG is 0, right? VSG is 0, and what we want is that my VSG should be greater than mod of VTH, which is 0.4 volts, and your VSG is 0, so it is not greater than that. So that means your MOSFET will be in off condition. That means your ID, you see, ID, it is 0 milliampere, right? This is what we saw. Okay, so what we saw was that when my VG is maximum, let's say 5 volts, my ID will be straight away 0. We have seen this, right, few sessions back, right? If you want, you can take a screenshot of it. Alright, I believe that you have taken a screenshot of it. In fact, I have clearly mentioned that over here. If you check this out over here, when my VG is 5 volt, then my ID is 0, okay? And if my VG is 0, then ID is maximum. We'll see that as well, okay? So let me change it to 0. So yes, you see motor starts running and there is some amount of current that we are getting over here. So when VG is 0, that means my VSG is how much? VSG is 5 volts. That means my VSG this time it is greater than mod of VTH. VTH is 0.4 volts in our case, right? That's why you see your ID, it is maximum. Let's say in this case it is 382 milliampere, something like that. I'll take it as maximum amount of current is flowing through it. Okay, so this is the overall idea. Okay, when your VG is 0, your ID, it has some value. That means maximum amount of current flows through the P MOSFET. Okay, in case of P MOSFET, I'm talking about P MOSFET. When your VG is 5 volts, your ID is straight away 0. Okay, in our case, just remember this particular point. What I'm trying to tell you all guys is that in our case, our VG, which is also equivalent to Vbias, right? Vbias was 0.02 volts, 0.02 volts, then I increased it by 1 volts, right? So my VG became, or rather my Vbias, it became 0.03 volts. So basically it is trying to, what it is trying to go towards 5 volts, okay? It is trying to go towards 5 volts, okay? That means my VG is trying to be positive, right? My VG is increasing, and as my VG is increasing, so my VSG will decrease, okay? And as my VSG will decrease, so what is going to happen? As my VSG decreases, okay, that means my ID or decreases, right? My ID decreases. If you want, you can just take a screenshot of it. This is the most important point that I have covered. Okay, so if you want, you can just take a screenshot of it. Alright, I believe that you all guys have taken a screenshot of it. So we'll go over here. I'll write this particular point over here as well. Okay, I'll just write it over here. Okay, in case of PMOS, let me change the color. Yeah, in case of PMOS, PMOS that we are dealing with, what exactly is happening is that my Vbias increases, right? My Vbias, it increases, and as my Vbias increases, so what is happening over here is that, what, just pause this video and try to think again. There shouldn't be any confusion in your mind. As my Vbias increases, that means my Vg of the PMOSFET increases. That means it is trying to go towards 5 volts, not exactly 5 volts, but it is trying to tend towards 5 volts. It is trying to go towards 5 volts. That means your Vg is increasing, so your ID, technically speaking, it is decreasing. ID should decrease. Okay, ID should decrease. Okay, and this is what I have mentioned over here. Okay, yeah, ID decreases as Vg increases, right? From as Vg increases by 0.01 volts. Okay, this is what we are seeing or we are experiencing over here. Also your VSG decreases. Why? Because your Vg, if your Vbias increases, that means your Vg of PMOSFET increases, so that means your VSG along with ID decreases. So these are the 2 points that you should focus upon. So this is what I had clearly mentioned. In fact, we are going to see that practically onto the LTSpice software. So let's check onto the LTSpice software. I'll just stop this. Okay, I hope you understood this thoroughly with the help of this particular example, and that's why, if you could recollect, you know, in the revisions, revision section, I intentionally simulated this particular circuit in front of you all guys, so that there shouldn't be any confusion in your mind, right? So anyways, we'll go onto the LTSpice software. I'll just erase this and I'll just cancel this out, and I'll just focus over here. Okay, and then over here you just click over here and put semicolon, so that the transient analysis won't be run henceforth. We just need to focus on this, that is DC sweep. Okay, and over here we are going to plot a graph between the Vbias. Over here Vbias is nothing but V3, right? V3 versus ID, that is the drain current that flows from the MOSFETs, both of the MOSFETs, right? Our start value should be, let's say, 0 volts, and stop value probably 1.8 at 1.8 volts, and it should be incremented by, let's say, 0.2 volts. Click on OK. Okay, I hope you know this particular part as well. The DC sweep, we have seen it. Okay, and then I'll just run it. Okay, so you see, one sec. So yeah, this particular x-axis, it represents the Vbias. Let me just show it to you over here. So this x-axis, you see this one, from 0 volts all the way till 1.8 volts, it represents what? It represents your Vbias. Okay, which is also known as gate voltage of PMOSFET, VGP, right? And what we have studied as, again I'm repeating it again and again so that you should not get confused, as the gate voltage of PMOS, it increases, right? In our case, it is increasing from 0.02 volts to 0.03 volts, right? As gate voltage of PMOSFET increases, so your VSG decreases, thus your ID also decreases, right? So basically, what kind of curve should we expect? Just pause this video and try to think. Okay, if I'm plotting, let's say this is my Vbias, and let's say if I'm plotting my ID over here, let's say this is my ID. So what kind of curve should we expect? Just pause this video and try to think. Alright, I believe that you all guys have tried your best. Now it's my turn to explain. So this is the curve that we should experience. That means my ID, I'm just showing it to you roughly. ID should decrease, something like this. ID should decrease with respect to Vbias. Okay, something like this. Okay, the value of ID decreasing with respect to Vbias. Let's verify it practically. Let me just erase each and everything. Okay, so let me just plot the graph for ID now. So for that, what I'll do, one sec, let me just move this dot model statement somewhere over here, so that it should be properly visible to you all guys. Okay, great. So now for that, what I'll be doing, I'll just hovering my mouse over here, Okay, and you see this kind of symbol, a black color symbol. Okay, again, see this is the red color symbol, and you just hover your mouse over this MOSFET, and you see the moment you see this black color symbol, you just click over here and you see you're getting this kind of graph. And if you could remember, this is my ID, and this is what I explained, right? This is what I explained. It's IS means nothing but this is your ID. Okay, this is my drain current of the MOSFET, the drain current which flows from both of this particular MOSFET, that is my ID. Okay, and you see it is decreasing, and this is what we assume, right? It should decrease with respect to this Vbias voltage, right? So this is my Vbias voltage and my ID should decrease, and this is what we are able to see. Great. So this is what we can clearly see over here. Okay, you see the ID decreases as my Vbias is increasing, right? ID is decreasing, and this is what I had clearly mentioned over here. One sec. As VG, that means my Vbias increases, my ID decreases, right? Great. So we are clear with this particular point. I hope this particular part is absolutely clear, guys. Okay, now you just focus over here. The second point, the NMOS is already operating at the edge of the saturation region. Okay, we know for NMOS to operate in the saturation region, this is the condition, that is VDS, it should be greater than equals to VGS minus of VTH. Okay, and VDS is 0.26 volts. Okay, and we know the value for VGS, it is 0.5 volts, which we calculated theoretically, and threshold is, it is given in the equation, it is 0.4 volts. That is my 0.26 volts, it is greater than 0.1 volts. So it is almost at the edge, right, of the saturation region, right? Now you might say that how exactly we got this particular value 0.26 volts. So for that, what I'll do, again, you just come over here and this time just delete it. Okay, if you want you can just take a screenshot of it. Okay, if you want you can just take a screenshot of it. Alright, I believe that you all guys have taken a screenshot of it. Now I'll just delete it. And I'll just zoom it out. Okay, and what I'll do this time, I'll just click on simulate. But before that, let me click over here and let me put one semicolon over here, so that the DC sweep won't be simulated, rather the DC OP will be simulated. So I'll click OK over here and I'll put somewhere over here and I'll just run. Alright, so you see you're getting certain values, but before that, let me just erase it and let me give the name of this node as VDS, and I'll put it somewhere over here, and let's find the value for VDS. Okay, so you just have a look over here, one sec. So the drain current which is flowing through the MOSFET, it is how much? 2.051 into 10 raised to minus of 5, so that accounts for 20.51 microamperes. Okay, now here is one more thing that we need to focus upon. First of all, we will focus on this value, ID of M1, that is the drain current which flows from N1 and M2. In fact, you go if you focus on M2 as well, it is same, right? Just the thing is that there is one negative sign. This negative sign indicates that this is my PMOS, right? So don't worry about that. You just have a look over here for NMOS. This is the value, the drain current ID. We'll focus on VDS as well. Don't worry about that. Okay, just have a look over here. It is 2 point. I'll just write this particular value somewhere. Okay, rather I'll prefer to write over here where we got the theoretical value for ID. So right now we are focusing on the practical value for the ID. So ID which we got from the LT Spice, right? So let me just write over here from LT Spice, from one sec, let me erase it and let me write it properly. From LT Spice simulation, right? From the LT Spice simulation, we are getting the value of ID. We are getting the value for ID as 2.051, something like that, right? 2.0513, something like that, into 10 raised to minus of 5. This minus 5, it represents 10 raised to minus of 5, right? Minus of 005, it represents 10 raised to minus of 5. Okay, just put this thing in your mind. Alright, so that means it is almost equivalent to 20.51 into 10 raised to minus of 6, which accounts for 20.51 microamperes, right? So quite closer to what we want. In fact, this is the reason that why we are getting some extra gain, because your value ID is, ID is almost 0. I mean, there is a difference of 0.51, right, in between the theoretical value and this practical value. So this is the practical value which we got, okay, from the LT Spice simulation, right? This is the practical value. I'll just write over here. This is the practical value which we got, and this is the theoretical value which we got. Now, just pause this video and just try to think in your mind that why exactly we got the difference of 0.51 between the theoretical and the practical value. We just pause this video and try to think. Alright, I believe that you all guys have tried your best. Now it's my turn to explain the reason. Okay, so the reason that why we got the difference of 0.51 microamperes between the theoretical value and the practical value is this. That is, you see the formula is absolutely correct, but we just for simplicity purpose we just didn't add this particular value, that is, we just didn't multiply this particular value 1 plus lambda VDS. Okay, to keep the things little simple, right, we just focused only on this particular part. We just avoided this particular part, but if you include this particular part, you see your current is almost equivalent to 20.51 microampere. On top of that, your gain will also increase, right? Okay, your gain will also increase. So that's the overall idea. I hope you understood this, that why exactly there is mismatch between the theoretical value and the practical value, not by huge amount, but certainly there is some amount of mismatch, right? So the reason is quite simple, because we have not included this particular value, that is 1 plus lambda VDS. The moment you include this particular value, your current will be almost equivalent to 20.51 microamperes, which is almost equivalent to the practical value which we want. On top of that, the gain will also increase from minus 1.33 to probably minus 137, right, which we got, right? Minus 137 which we got. So that's the overall idea. Okay, I hope you understood this particular point. Now again we'll come to this particular part, that how exactly we got the value for VDS. Okay, so you see VDS is 0.26 volts. So just have a look over here. The VDS, it is how much? One sec, it is 0.26, right? 2.5 means 26. You can consider this as 26 volts, right? So VDS is how much? 0.26 volts, and that's what I have mentioned over here. One sec, let me just add over here as we. Okay, so you just have a look over here. This 0.26 volts, it is greater than, it should be greater than 0.5 minus of 0.4, so that is 0.1 volts. So yeah, this particular NMOS, right, this particular NMOS, this one, it is operating in the at the edge of the saturation region, right? This particular NMOS, it is operating at the edge of the saturation region. Okay, now if and this is for 0.02 volts, when my bias voltage, it is 0.02 volts, right? Now as soon as I increase my bias voltage, let's say from 0.02 volts to 0.03 volts, right, your this VDS decreases, right? We'll see that. So I'll just cut this, and I'll just increase the value of V bias voltage. Let's say from 0.02 volts, I'm increasing it to 0.03 volts. Let's check the value for VDS. Let me just run it, and the value for VDS, it pans out to be how much? 0.15, right? So you see the VDS decreases, right? VDS decreases from 0.26 volts to 0.15 volts, right? Something like that. And this is what I had clearly mentioned. Although it is still in the saturation region, but the value of VDS has decreased along with IDS, right? Along with IDS. Okay, I hope this particular part is crystal clear. Along with IDS, the value of VDS also decreased. Great. So now if I want to express this in over here in the drain source characteristic of NMOS, so it is the drain source characteristic of NMOS. So I'll just give you a rough idea. So let's say when, let's say over here, let's say this is my V bias, which is equivalent to 0.02 volts. Okay, when my V bias was 0.02 volts, right, at that time my VDS was how much? My VDS was, rather, one sec, I'll write it in this way so that there shouldn't be any confusion in your mind. Okay, let's say my VDS was, one sec, yeah, let's say my VDS it was equivalent to how much? It was equivalent to 0.26 volts, right? VDS was equivalent to 0.26 volts, and my ID was almost equivalent to how much? 20 microamperes. Let's say 20 microamperes approximately. Exactly, it is 20.51, right? And I have explained you the reason for that. Okay, and when we were getting this particular value, when this Vbias was 0.02 volts, right? Okay, then what we did, we just increased the Vbias, right? We increased the Vbias voltage, right? We increased Vbias voltage by 0.01 volts, and the moment we increase Vbias voltage, what we know is that as my Vbias increases, right, that means my VGP, right, which is equal to VGP, gate voltage of PMOS, increases, so my VSG decreases, and VSG of the PMOS decreases, and as VSG of PMOS decreases, so the ID also decreases, right? And as ID decreases, we also found out that as my Vbias increases, so VDS of NMOS, it decreases, right? From 0.26 volts, it decreased to 0.15 volts, right? 16 to be precise. So VDS also decreased, right? So in the next scenario, when I'm increasing my bias point, right, what exactly is happening? My VDS, which was 0.26 volt, it decreased. Okay, also ID also decreased, right? Along with VDS, my ID also decreased. So this is how I'm going to show. This was my ID, let's say 20 microampere. From 20 microampere, my ID decreased. Okay, along with ID, my VDS also decreased. So my biasing point will shift downwards to the left side. Okay, that means somewhere over here. Getting this particular point, it is very, very, very important, guys. Again, I'll just quickly revise. As my biasing point, or rather my Vbias of the PMOS increased, right, VSG decreased. Okay, with VSG, along with VSG, my ID also decreased. Okay, and we also saw that with the help of simulation, as Vbias increased, right, the VDS also decreased along with ID and VSG, right? Okay, so you see, this is how I'm going to frame it over here. My ID decreased from 20 microampere to, let's say, 19 microampere, or let's say 18 microampere, whatever that value is. We don't need to focus over that, right? So as my ID decreased, so I'll put the value of ID somewhere over here. And then we also said that along with ID, my VDS also decreased, right? So over here, this is how you're going to show over here. So basically your VDS will shift downward left side, right? Somewhere over here. Getting this particular point, it is very, very, very important, guys. Okay. Okay. So I'll just frame it over here. So this is the value VDS. Okay. VDS, and over here VDS is how much? VDS is 0.155. Okay. 0.155 volts. Okay. And let's say ID. Okay. Let's say ID is, let's say it is maybe 19 microampere or 18 microampere. Just for our understanding purpose, we are taking it as 18 microampere. We don't know. Okay, but we have seen the graph of Vbias versus ID, wherein we saw that the ID decreases as my Vbias increases, right? Okay, and this is happening when my Vbias has increased by 0.01 volts. So Vbias is 0.03 volts. So this is the most important key point that we need to remember. My biasing point shifts, right? And what will happen if my biasing point shifts? So you see over here, earlier we were able to obtain a signal of, let's say, a signal with a gain of 133 minus of 133. Okay, all right, we were able to achieve this particular gain. But over here, you see, as my biasing point shifted, right, as my biasing point shifted, so you see this waveform got clipped over here, and we were unable to achieve the proper signal, right? So this signal is kind of distorted. signal which we got, it is distorted. So this particular signal, it is distorted signal, distorted signal. Okay, so you see this lower part, it is getting clipped, right? Something like this. So your actual signal will be something like this, but this particular part, it is getting clipped over here. And why it is getting clipped? Because your biasing point of PMOS got shift, Vbias got shift. Okay, and as it got increased, or as it got shifted, or as it got incremented by 1, so your ID along with VDS got decreased, and thus you see we are getting this kind of waveform which is clipped, right? So what we can conclude over here? We can conclude that your gain is highly dependent on this particular biasing point, right? Your gain is highly dependent on this particular biasing point. Okay, I'll write this particular point. This is the most important point that we need to figure out over here. Okay, and let me just write over here properly. So let me just write over here the points that we just focused right now, which we concluded rather. So this was the very first point, that is the gain, that is AV, right? The gain, it is AV of the circuit, of this particular circuit, of this circuit, that is CS amplifier with a current source load. So gain of this particular circuit is dependent on the biasing point, is dependent on Vbias, right? That is the biasing point, Vbias, right? It is heavily dependent on that, right? So if Vbias shifts, your gain also changes, and thus we get this kind of distorted signal which we just saw, right? And so basically we need to design a circuit, okay, or rather we need to modify this particular circuit, okay, so that our gain does not depend on Vbias, right? So let me just write this particular point, although this is the point which we are going to see in the upcoming video, so don't worry about that. So we need to modify this circuit such that the gain AV, so this gain AV, it becomes independent of Vbias, right? Is such that AV is independent of Vbias, right? So we need to modify that particular circuit accordingly, right? And to make AV or the gain independent of Vbias, we introduce one concept which is known as a diode connected MOS. So let me just write this particular point as well. So AV becomes independent of Vbias when we introduce a new concept which is known as a diode connected MOS, right? So AV, that is gain, let me write it in this way. So gain, that is AV, becomes independent of what? It becomes independent of Vbias when we introduce a new concept, known as this, that is diode connected MOS, diode connected MOS or MOSFET, whatever you want to say, diode connected MOS. So just by using this particular concept, we will see that how exactly we make AV independent of Vbias, right? So don't worry about it. But I really hope that you understood each and everything up till here. If you have any doubts, if you are facing any difficulties anywhere, just make sure to ask those particular doubts into the communication section. I'll be happy to help you out there. So thank you for listening patiently. I'm ending this video over here, and then in the next video we are going to see that how exactly this CS amplifier with a current source load, it provides high gain as compared to the simple CS source, common source amplifier, sorry, as compared to CS amplifier, right? So this was all about the session. Thank you.